No, I will not be here tomorrow. They must. I can fix it right now. Are you still open today? Okay, either or change tomorrow to the testing center. Do you know how to do that? Yeah, so she has it already, so you go right in there. So just, yeah, just schedule the testing center. Thank you for letting me know though. That happened a few times last year too, where they had it like backwards.
I don't choose it.
Okay. You don't have to clap back, but when I clap, you've got to stop. Okay? That's your signal to stop your conversation, come back up front, ready to move forward. Okay? Okay, 2 quick announcements, and then we'll jump into our lesson today. So number 1 is just a reminder, and I know I'm somewhat preaching to the choir because you are the people here today, not absent. But in case you are ever absent, I just want to remind you about the resources available to you. Okay, so the best thing to do if you're ever absent from this class is to go to Canvas and to click on the What is Happening Today page. Okay, so you click on the page itself. I do not recommend, and I would say this for most teachers, like don't just go to the to-do list of what do I need to get done. Because all the to-do list is going to have is the homework assignment, and you'll have no information on how to actually do it. So if you click on the What's Happening Today, so this was from last time's class, if you click on that page right there, it will show you what we covered. So first off, if you see you missed a warm-up, that means you need to talk to me because you're missing some of those points. Figure out how to make it up. Okay? It'll let you know any announcements we covered of due dates and things. And then the big thing is it's going to have a video like I'm filming today of the actual lesson. Even though I do it, like, I think it's good when a student like goes to their friend, they're like, hey, I was gone, can I get the notes? Honestly though, how much do you learn from copying the notes from a friend? Do you learn anything? I'd say most of the time, no. You just literally completed a task, but in terms of actually learning the information, you probably didn't get anything. And so sure, you can do that, but I need you to come here and watch the video because then you'll actually get the lesson that you missed. That is also how you'll make up your engagement points, because if you're gone from class, you lose your engagement points. But to get those back, you just have to come to me and show me your completed notes, as well as somewhere in the video, I give out a random code word that you give me as well. That shows me you watched the video, but then that way too. Okay? And then, of course, it would tell you what the homework is. But please use those resources if you're ever gone to help you not just get the information, but hopefully learn the information. And then always, of course, though, if you watch the videos and you're still confused, come see me. I get from a video, you still may not get all of it because you have questions. So it doesn't have to be perfect, but make sure you do that first. Okay? All right, so with deadlines, the thing I wanted to remind you about, I've posted it back there on your guys' side of the calendar. So the Unit 1 quiz retakes are due next Tuesday. Okay, so you have all this week up till next Tuesday to retake the Unit 1 quiz if you're wanting to do that. Remember, you have to go through corrections first, get all the help you need on those, then you can actually retake it. For retaking it, you can obviously schedule with me, or you can also do it in the testing center. So if you want to do it like on 8A or on a Wednesday when we don't have Sky Time, you can go to the testing center. It's room E303 or 2, somewhere in that area. And you just go there and you just say, hey, I need to take Mrs. Alviso's Chemistry Unit 1 quiz retake. And she'll set you up. You'll take it. I'll get the results. You have to turn in your corrections to me, so don't give them to her. It's just easier if you give them to me. And then that will replace your original score. Any questions on the retake process? Okay, so just a reminder, if you are wanting to do that, next Tuesday's the deadline. Once that deadline passes, then the scores will stay as they are. Okay? Okay, close your eyes really quick. I just want to ask one thing, but I want it to be anonymous, so no one feels pressured in any way. So close your eyes. Heads up, 7 up. Okay, out of curiosity, and once again, no pressure, I just want to know, who is still working on the Smiley Face Habit Challenge? Like you haven't fallen and broken off yet. Okay, hands down, eyes open. Awesome. That's quite a bit of you. Good job, guys. So keep that up. Okay, so let's jump into this. Okay, so in our discussion today, once again, it's all about the types of radioactive decay. So the first thing you need to understand are the particles themselves, because the particle's identity helps you understand what's coming out of this nucleus. And if you understand what's coming out, then you can understand how it's going to change. Okay? So we mentioned these last time, but today the goal is you need to know them by symbol. Okay? You need to be able to see this symbol and be like, oh, that's gamma. That's a positron, that's a beta, and that's an alpha. Okay, so these are what their nuclear symbol looks like. It's very similar to the nuclear symbols we looked at last unit, where the top number is a stick. Okay, so if you want to label to help you remember, so the top number is the mass, just like before. So an alpha particle has a mass of 4. So again, this is, we could blow up an alpha particle, it would maybe look something like this. Okay, and remember what the bottom number represents? The proton number. Now the different part is here is outside of alpha, alpha actually is an atom. It's a helium. A helium nucleus is the difference. It doesn't have any electrons on it. But the bottom number 2 represents the proton number. Okay? And then the number out front represents the charge. Okay, so hopefully that rings a bell from what we did last unit. Okay, so this right here, once again, alpha particle, mass of 4, 2 neutrons, 2 protons, positively charged. Okay? All right, our next one is known as a beta particle. Now a beta particle has 0 mass. Okay? No mass to it. Hence the 0 at the top. It's a little weird because the bottom number is a -1 because of what it represents in terms of its relation to a proton. I'm going to use this green ball to represent a beta particle because it's completely different from a neutron and a proton. Okay, it really is like an electron. Okay, and we'll come back to that in a second. So there's our beta particle. Okay, a positron, a lot of times you can think of it as it's kind of opposite of the beta because the symbol's almost the same, except for it's a positively charged electron-sized particle. So same size as the electron, but positively charged. Okay, so we'll use this red ball to represent a positron. Okay? Okay? And then our last one is the gamma radiation. The difference here is it has no mass and it's not a particle. It's actually just pure energy. This symbol right here kind of looks like a Y. It's a Greek letter. The Greek letter is gamma. When I draw it by hand, was it printed on your notes or are you having to draw it in, that symbol? When I draw it by hand, once again, it kind of looks like a Y. I often go, because that's kind of what it looks like. It has like a little loop in it. It'd be kind of hard to see in that bolded notation. So that's the sign for gamma. Gamma is just pure high energy. This, as we mentioned last time, how some radiation is harmless. Other radiation can be quite dangerous. Gamma is the kind that we worry about. because it is what can change your DNA, hence cancer, right? Because that's how cancer is made, is when your cells get mutated. So, okay. And you can see that from the thickest material they go through, right? So an alpha particle can't pass through paper. They're too big, right? So if I have my Geiger counter out here, let's turn it on here. So remember how it beeps every time it picks up radiation? So I have a radioactive sample here, so it beeps a little bit more. Okay, so if I put a piece of paper in front of the sample, so everything that it's detecting is not an alpha. Because if it was an alpha, it wouldn't be able to go through. Hence, this is actually a beta sample, so it's emitting beta particles. But on that side, with beta and other ones, lead is what can stop those ones, and then combination, it's really like a combination of lead and concrete to try and stop gamma. Can anyone think of a real life application where you've seen lead used to stop radiation? Caleb.
X-rays, like at the dentist.
Great one, Caleb. Have somebody for it. Yeah, when you get an X-ray at the dentist or at the hospital and they put that big heavy blanket on top of you, that is lead. And so they're stopping any radiation to go through you in the areas that you don't want to go through you, right? There's also a good reason why they don't do X-rays anymore on certain parts of your body. Like, it's pretty rare to actually get an X-ray of your head these days. Instead, what do? Yeah, they'll do an MRI or CAT scan because it's differently. Sadly, we've found that even though X-rays are awesome and they can give us good information, it's not healthy to send it through certain parts of your body. Also, like if you get pregnant, you can't get an X-ray while you're pregnant because they don't want to send X-rays through the baby. Because obviously, once again, even though it's great, there's a reason why the nurse who's doing the X-ray, where do they go when they turn on the machine? They leave the room, right? Like, they don't want to get exposed to too much radiation, okay? All right, questions on our 4 types of particles. So now what we're going to look at here is that if this is my unstable nucleus, and it goes through an alpha decay, what's left behind? Okay, so that's kind of our next step, is the putting it together and balancing it out, okay? Here's just a picture once again showing that idea of them being able to pass through versus getting stopped along the way. Okay, so our first example here is an alpha decay. Now keep in mind, the way we read a chemical equation, we'll look at these all year, okay, is your thing on your left is considered your reactant, or in this case we call it the parent nuclei. Okay? The arrow represents the change it's going through. Now in chemistry, the arrow is like an equal sign in the sense it has to be balanced. It's not like an equal sign in that the way it's pointing does make a difference. It's saying this becomes this plus this. So it's like it was together and now it's separate. Okay? The thing that it creates is known as the daughter. Sorry, we don't ever call them the son. I don't know why. They're always daughters. Okay, but the thing that it turns into is the daughter nuclei. And then the particle is whatever particle was emitted in the process. Okay, so I have uranium-238, like this. Okay, it'd be much bigger if it was uranium, but I didn't want to build that big a model. Okay, when it undergoes alpha decay, it's going to emit an alpha particle. So now, how do I know what's left? What do I look at? How do I know?
What you got rid of?
So first off, what did we get rid of? Taylor?
Where did it go? I didn't
It's
see
right,
it.
Sam's holding it.
Oh. You got rid of 2 protons and 2 neutrons.
Okay, so if I was uranium and I had 92 protons, if I get rid of 2 of them, how many do I have left? 90. Now what does the top number represent? The mass. So how much mass has this nucleus lost? 4, because protons and neutrons together. So the mass is now 234. And how do I know what it is? What's the daughter? Colin? Very good. So Colin noticed, well, our proton changed, which means our substance changed. So I come over here and I find element 90, thorium, and And that's what it's turned into. So we would say that thorium is the daughter from uranium. Questions on how I did that? This is what it means to use the law of conservation of mass and balancing equation. Jackson, how does my face? I did not mean to hit you.
Oh, no.
There's a reason I coach running. I can't row. And the other sports I played soccer with my feet and I swam. So like, yeah, not good. Okay, questions on that? Okay, let's take a look at, we'll do the top one for beta.
Just kidding.
Where's my grease? Disappeared. Okay, now, same concept. Here's our parent, iodine 131. This time we're emitting a beta particle. Okay, so beta particles have 0 mass, so what's going to happen to my mass? It's stay the same. I'm going to write it right here because I can't reach them high. So 131, the mass is the same. Now what's happening with the proton number to make this equation balanced? Anyone have a thought? Why would I add one, Sam?
Because you have to make the weight 0, and so if it has a negative one, you have to add it to make it. You just have to add one to make the mass 0.
You gotta pay attention where the arrow is, everybody. Notice this, okay? Ice. Will you come sit by Caitlin, please? We're just getting a little too distracted. Okay, so notice this is my equal sign. Okay, if you thought to -1, it's fine, because this is the first time you're seeing it, but that's the most common mistake, is they see, oh, -1, so they'd say 53 minus 1 and put 52 here. This is my equal sign, okay? 53 equals what plus -1? So in order to make it equal, it actually goes up in number, because 54 plus -1 gives me 53. Everybody see that? So the biggest mistake is to not pay attention to where the arrow is. Now, let's talk about how this works in, real life. This is the symbol. Okay, I understand math. But, first off, what's a beta particle?
The green one.
A green one. It's coming out of here. Do you see any green ones in here? And by its symbol, what is a beta particle like?
Electron.
It's like an electron. Are there electrons in the nucleus? Last we talked, right? No. So it gets a little weird here in that the molecules themselves break down. So what's the charge of a neutron? They're neutral, right? They don't have a charge. So this is a rough explanation. It's more detailed than this, but it's a good starting place, okay? Pretend a neutron, and I wasn't able to figure out a good way to model this yet, but a neutron is neutral because this is made from something positive and something negative. Does that make sense, right? If something is neutral, half of it could be positive, half of it could be negative. Together, it's neutral. So what happens in a beta decay is a neutron splits in half. I didn't want to use a red one, actually. I want to use a new proton. Okay, so negative, positive. This is this yellow one. Okay, in a beta decay, the yellow one breaks in half, kicks out the negative, and leaves behind the positive. And now do I have more or less oranges than I started with? More, which is why the orange number went up. The proton number increased because it split in half. Questions on that? Yeah, take
I
it.
don't want to go too much into detail, but with the mass change too, technically it's being split or not really?
So it's not quite a split in half, because you remember that a yellow and an orange had the same mass?
Yeah.
So the part that it splits and kicks out had no mass. So that's why the mass stayed the same. It's because this had the same mass as the yellow one. That's why I haven't quite figured out how to make this into a model. I don't know, maybe I'll cut them. But the green will be a teeny, I don't know. But yeah, does that make sense? Yeah. Cameron. A neutron. Yeah, so one of the yellows, so this was here, so this was our before. One of these splits, kicks out the beta, leaves behind a proton. So in a sense, that's why like the mass is the same, is because this, does that make sense? Okay. Any other questions on beta? Okay, let's go to positron here. Okay, so positrons have 0 mass, so the mass will stay, oh, we've got to identify, what did it turn into? Yes, XE xenon. Once again, look at the bottom number, go to the periodic table, XE. Okay? All right, mass is going to stay the same. Now, pay attention to the arrow here. Oh, yeah, Oliver. So the nice thing is you can always check it. So let's see. So if I put 20 here, 20 plus 1 would give me not 19. So what do I want it to be? There you go, good catch, Oliver. Have a smiley face. And once again, it's totally, it's easy to, like, these are very simple mathematical problems, right? You're adding 1, you're taking away 1, you're adding 4, taking away 4. The tricky part is not just getting too caught up in the math and forgetting about, like, what's actually happening, right? Good. How do I know what element that is? Good. I see everyone's eyes looking here on your table. So argon is the daughter. Questions on that one and balancing positron or beta? Okay. All right, so the last one we need to talk about is gamma. But if you recall, gamma is not a particle. It's just pure high energy. And its symbol is 0, 0. So technically, when something emits gamma, it doesn't actually change what it is. Because you haven't changed your protons, you haven't changed your neutrons, and so it actually stays the same. And in actuality, what happens a lot of times with gamma, what it's doing, it is releasing energy to become more stable. You could almost visualize it as maybe some extra rubber bands, right? Remember our cartoon we watched last time with the protons and the neutrons and the rubber bands holding them together? That gamma is kind of some of those extra rubber bands coming flying out to try to get more stable. And often it happens in link with other decay, right? So when an alpha decay happens, it could also be releasing gamma at the same time. Or same thing, when it undergoes beta decay, it also is releasing gamma at times. And so we have no change in mass, so you're actually never going to have to balance a gamma because in a sense, nothing changes. But I do want you to understand that it is there in this process. Okay? And then vocab word transmutation is this process of one element becoming another. When it changes from one thing and actually changes to another element is known as transmutation. Kind of, you'd also link it to like the word transform, other similar words like that. Okay, 3 smiley faces. Work with your table and try these 3 problems out, and then we'll check them. Okay, ready, set, go. Try it on your own and then compare with your table, see if you get the same answer. Once you're done, check as a table, see if everybody has the same, if they don't, help each other out. The phosphorus. Oh, I did it wrong. I didn't write it. How do you feel?
So kind of like right out.
Yeah, so the biggest thing is just paying attention to where's the plus sign and where's the arrow. Right, so like in this one, okay, we want to add them together, but on this one, the arrows are here, so it's like what plus what. And that's really like, the math's easy, but that's where people get mixed up. Good job, guys. Go ahead and set your pencils down when you're done, that way I know you're not thinking anymore. Yes, so it's saying radon is undergoing an alpha. So when something decays, are things breaking off? It's kind of tricky to say add or subtract, so it kind of depends when you're looking at it. But go ahead. Yes, you can think about it that way. Or you could say this loses out, so minus it. This equals helium plus.
So really, because wouldn't it be like that?
So is radon losing or gaining? Yeah. You're good. Okay, does anyone need another minute before we double check our answers? When it says decay of this, that's the starting point. And then it's going under decay, so let's do that. If it was the other way around, it would say maybe like, what was the parent isotope of this daughter when it underwent alpha? Does that make sense? The difference?
Oh, could we write that?
Yeah. So let me answer this one there, because you might not be the only one to have that question. All right, give me your attention here, everybody. So I want to bring up something, and then so if you have this for your first answer, have a smiley face. Okay, well done. Any questions on the first one? Okay, second one, you should have 35, 15, and that's the phosphorus. You have that, have a second smiley face. Any questions on that one? And then the last one is having you do all the work of the whole equation. So you should have done, okay, radon is Rn 198. I come over here to find its proton number. Alpha decay means that this is breaking apart, right? A piece is flying out hitting Jackson. Okay, that piece specifically is an alpha. If it said beta, then I would have used the beta particle. Okay, but it's an alpha. Plus, make it balanced of the thing that is left behind. Okay, because once again, so it was this. This flew out, and we now want to know what's the daughter. What did it turn into? Okay, so the daughter would be 194, 84, which is PO. Is that right? Okay. Now, Jane brought something up that I want to discuss with everyone because maybe you also had this thought. And tell me if this isn't what you asked, Jane, but you asked along the lines of why don't we just show it minusing instead of like the adding thing? So and this is something that is like a fundamental pattern, in the world of chemistry, our chemical equations never have minus signs, ever. It's only ever addition and arrows. But the placement of the arrows, in a sense, is what's indicating where it's going. My biggest thing why I think is the idea of how the minus might indicate like it's going away. And it's not really going away, we're just showing it was this, and now it's these two separate things. Versus like, so you'll never actually see minuses ever in a chemical equation. You're only ever going to see pluses. So, great question, I was smiling face for that. Sam?
So you talked about how the reason they released like all these particles is to become stable.
Yeah.
Isn't like the law of thermodynamics where it's like entropy, where everything wants to become unstable in the universe? So why are they trying to become stabilized?
So entropy's not quite about, it sounds similar to stability, but it's not about stability in that it's disorder. And disorder is actually more spread out things are. So actually breaking down does increase entropy. Because one particle has less entropy than actually two particles does. Even though like it is more stable now. Does that make sense, the difference? Yeah, great connection, Sam. Any other questions on this process? Okay, I think, last thing. So I just want to connect it back together, and you'll see one of these on your homework. And then the rest of the time, you should have plenty of time to get your homework done in class. Okay, so let's connect this back to our graph that we looked at last time that Shaylin reminded us about. Okay, so in this question, the question says, this isn't on your notes, by the way. This was just something as I was prepping for the lesson, I was like, I want to bring this back because you'll see it on your homework. Okay, so the question says, write out the nuclear equation to show the daughter nuclei that is formed when zirconium-80 decays. So the first step here is you have to use the graph to identify what type of decay zirconium-80 is going to undergo. So, reminding from last time, what's the first thing I need to find out with zirconium-80? ZR80. What do I need to know to use my graph? Protons and neutrons. So find zirconium on your periodic table. It has 40 protons. So I'm going to come here. How do I find neutrons? Subtract. It's not 80. Okay, the most common mistake on the test is people forget and they go 40, 80 because it's zirconium-80. You got to minus it to get to neutrons. Okay, so 40, 40. Okay, so I'm in the positron emission category, so that's the particle I'm going to use. So I'm going to show, okay, this releasing a positron, because that was the section I was in, and then we need to balance to find the daughter. So the mass was 80, positrons, no mass. The mass would still be 80. But then to make it balanced, what does this number need to be?
39.
Yeah. 39 plus 1 gives me 40, which means it turns into yttrium. That's neat. Yeah, Jane.
So how does Nata make a positron?
So positrons like beta are another one that are made through the breakdown of a neutron or a proton itself. Let's see, because this one is a proton actually breaking down. So a proton breaks down, kicks out the positron, and ends up leaving behind a neutron, which is why the mass didn't change, but the proton number went down. It's because this broke up. So it's another one, yeah, that's messing with the quarks of the insides of them. So great question, Jane. Any other questions on this? Okay, so your homework tonight, Ellen, can I borrow yours real quick? Yeah. Is this one nuclear decay? There is a backside, so don't just do the front and turn that in. Front and back. You got like 30 minutes to get this done, so you shouldn't have any homework tonight, okay? Until this is finished, you shouldn't be on your phone, okay? And you shouldn't be doing anything else. Once it's done, then you are allowed to check it, check your answers online, and submit it. Okay? Any questions? Okay, let me know if you need help as you work, okay?